wonderful person, this is Anton, and in this video we're going to be tackling one of the most fundamental questions in particle physics. Is there anything inside a quark? And that's because for a very long time, based on our best understanding of the universe, and specifically based on something referred to as the Standard Model, researchers always believed that quarks are elementary particles, meaning that they have no inner structure and are not made of something smaller. Or basically, there is nothing beyond the quarks, at least based on the Standard Model of physics. But one of the recent experiments from the Large Hadron Collider, and specifically the CMS collaboration, something you can learn about in one of the studies in the description, for the first time in history, essentially pushed the boundary of how small of a thing we can actually see, in order to find out if that hypothesis and this proposition is actually true. And so let's discuss a little bit more about this, but first, in order to understand why this is important, let's first discuss just a little bit of history and how we've discovered all of this. Or basically, why do we even have this standard model of elementary particles? And technically here, the history goes back thousands of years. Because back in the days, before we could even perform these experiments, even ancient Greeks believed that ordinary matter seems to be composed of something that's very difficult to see, but that seems to be indivisible and does not contain anything inside. They refer to this as the uncuttable or indivisible matter, which in Greek is atomos, and that's where the word atom came from. But their factual existence remained more or less controversial up until 1905. This is actually when Albert Einstein published his paper on Brownian motion and was able to prove that molecules were not just mathematical illusions, but actually existed. And soon afterwards, Ernest Rutherford discovered that they were not indivisible at all. As a matter of fact, even atoms in this case seem to contain a dense nucleus inside of them, right in the center. And so following these early experiments, pretty much every single year, something new was discovered about some of these particles. And some of the first discoveries from the nucleus were made just a decade afterwards. And so basically by 1919, researchers confirmed the existence of protons, and by 1932 they also discovered neutrons. But some of the biggest breakthrough was actually made in 1968. This is when physicists realized that even these protons and neutrons were actually made out of something else even smaller. This was the discovery of quarks. And so every time scientists looked deeper and deeper and tried to create something with more and more energy, they seemed to discover new layers. But by 1970, the Standard Model essentially codified the existence of most of these fundamental particles. And so for the past few decades, all of these subatomic particles can essentially be summarized in this image. We basically have 17 distinct elementary particles, with the last one, the Higgs boson, only confirmed to exist back in 2012. But pretty much all of them do something different and are even fundamentally different in how they react with everything else. For example, 12 of them are known as fermions. These are electrons and quarks, which form the matter as we know it. But 5 of them are bosons, which are a little bit more difficult to imagine because their job is to essentially carry forces. So things like the strong force, which basically holds the atom together, seems to be produced by these mysterious bosons. But quarks, which are of course the smallest particles inside the atom, are also unique because they seem to come in 6 unusual types. For reasons that I still don't really get, these are not actually known as types, but are known as flavors. And the flavors are up, down, charm, strange, top, bottom. Intriguingly, what makes these particular particles particularly special is the fact that these are the only particles that seem to feel all 4 fundamental forces. They feel the gravity, they feel the electromagnetic force, and they feel the weak and the strong force. In comparison, something like a neutrino can only feel 2 forces, gravity and the weak force. Alright, yeah, I know things are getting a little bit more complicated and a little bit more technical, but the main point here is that, well, that's kind of what these fundamental particles look like as of 2026, and today we believe these are the basic building blocks of everything in the universe, with the assumption being that they are possibly like point-like entities with maybe no size at all. As a matter of fact, we have no idea what they even look like if you look at them super close. But naturally in science, it's always important to kind of stay skeptical and to possibly test some of these propositions and some of these ideas. And so if history were to repeat itself, maybe even quarks could be composed of particles that are even smaller. And this has been previously proposed with the name Preon, proposed as a potential explanation for these even smaller point-like sources that could actually be the true fundamental building blocks of all matter. This was proposed back in 1974 by Jojeshpari and Abdus Salam, and they were mostly intended to explain the large number of existing particles and their properties. But for over 50 years, they remained unproven. Although if they do exist, they would simplify this particle zoo and would explain everything in a much more elegant way. And that's essentially what this new experiment was trying to test and to find out. Do preons exist, and can we possibly find them? And so to test this CMS detector at the Large Hadron Collider was used to collide protons at incredibly high energies. This is in essence what this whole study is about. And that's because by colliding protons at these energies, there was maybe a slight chance that some of them would not just produce quarks, but would also break apart quarks as well, that could then produce preons. And in this experiment, scientists specifically focused on something called D-jet angular distribution. Yep, more technical stuff. I mean, technically you can skip this part by using the thingy below. But in essence, this is a kind of a tool in high energy physics that tries to find new phenomena by measuring the scattering angle resulting from the collision of two extremely energetic particles. And so if there's some kind of a new interaction or some kind of a new unusual particle, it will often produce collisions with angles that don't match expectations and previous theories. In other words, this is a great technique because it seems to be very sensitive to new physics. And so when quarks scatter, they're supposed to create jets, which are kind of like sprays of particles that fly out in different directions. And so by measuring the angles at which these jets fly out, researchers can then tell if quarks are behaving like smooth point-like dots, or if they possibly have something inside of them as well and are made out of individual particles, which would produce different angles. And that's because they would break apart and scatter in a different way. And so here the results from the study used a lot of data collected between 2016 and 2018, focusing on probing quarks down to a scale of about 10 to minus 20 meters. And just to give you a better understanding, that's approximately 10,000 times smaller than a typical proton. Okay, so what did they find? Well, at this scale, right now there is absolutely no evidence that something seems to be inside or that there is any kind of an inner structure. Or essentially the data shows that quarks still seem to be point-like and seem to scatter as if they had nothing inside, with all of these scattering angles matching the predicted value from the standard model perfectly. With this experiment right now setting the most stringent limit on this so-called quark compositeness, with the overall conclusion from the study being that if quarks do have something inside and if these preons are real, it can only be revealed if we actually use even higher energies of at least 37 tera-electron-volts. Or basically it would require even more powerful collisions. But this experiment didn't just look for quarks and preons, it also tried to find something else beyond the standard model, or something that possibly did not match predicted values. For example, some kind of an extra spatial dimension, some kind of a quantum black hole, or maybe some kind of a sign of dark matter. And while they did find some kind of a very small difference in the data for some of the high mass regions, they also determined that none of them were significant enough to claim a new discovery. And so overall, as of mid-2026, the standard model of physics seems to be more or less correct. And though it is maybe incomplete, right now this is the best model we have to explain what everything is made out of, and to of course explain the entire universe. Although just as a small side note, when it comes to these predicted preons, while still highly speculative, a lot of previous models proposed that, in terms of size, they technically could be much smaller than what scientists were testing for. Compared to what was tested in this study, they might actually be at least 10,000 times smaller, implying that maybe these collisions were just not powerful enough to break these quarks apart and to create these even smaller particles. And so if the existence of preons is confirmed, it would definitely revolutionize particle physics. But nevertheless, this experiment definitely did not discover anything. Nevertheless, these experiments are still quite important, and in this case, for reasons we discussed in a lot of previous videos. For example, the standard model still cannot actually explain gravity. And I mean, gravity is one of the biggest forces in the universe, yet somehow it's completely missing from this picture. None of these particles, and of course none of these bosons, can physically explain how or why gravity works. And though Higgs boson that was confirmed in 2012 explains how some of the mass is produced, which can then lead to the explanations of gravity, it actually only explains like 1%. 99% of mass is unexplainable right now, which is something we discussed in one of the previous videos in the description, and something we'll be talking about very soon because there has been some additional research. So, subscribe and stuff, because that video is coming out really soon. But apart from gravity, it also does not explain dark matter, it does not explain dark energy, and cannot even explain why there is more matter than antimatter in the universe. In other words, some of the biggest questions and some of the most profound questions cannot be explained using this somewhat simple particle model. And so by cracking a quark and by finding a structure inside of it and possibly discovering some kind of a new subatomic particle could potentially lead physics to a new complete theory of almost everything. Which means that the search is not over yet. While this particular experiment didn't discover anything, just as I mentioned before, this was from the data from 2016 to 2018. Which means that there's a lot of data that has not been analyzed yet, and the current third run has not been analyzed and has not been studied. As a matter of fact, some of the future data, and especially from the High Luminosity Large Hadron Collider, may allow us to probe even smaller scales and higher energies. Which means that maybe, just maybe, in the next few years, we might indeed discover that quarks are not the end of the line. We might find that next layer of reality, which of course would be groundbreaking for modern physics. Or alternatively, maybe, all these additional experiments will just confirm that quarks are indeed the smallest possible subatomic particles. Which means that a lot of those other mysteries like antimatter and dark matter have to be studied in some other way that we obviously do not know yet. But based on this study, right now we can confirm that quarks seem to be the smallest constituents, there seem to be no hidden or extra dimensions in the universe, there seem to be no dark matter particles discovered in any of the collisions, and there were no axion-like particles or quantum black holes. And so here, by analyzing these very specific angles following collisions, researchers definitively showed us that we can test a lot of physical concepts by just looking at some of this older data, which means that we'll come back and discuss additional data and additional discoveries in some of the future videos. On that note, thank you for watching, subscribe, come back tomorrow to learn something else, support the channel on Patreon where you can find additional videos without any ads and can DM me directly, or by joining channel membership that grants you early access. You can also support this channel by buying the Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.